Welcome everyone. This will be one of the first videos in a series related to natural language processing. We'll go through how LLMs work, how agents work, how RAG works, and so on. Just a disclaimer, this series is heavily dependent on CS2 to 4N. It is the part of my learning process. So I'm learning it, going through the slides and lecture notes in detail and preparing my own notes. And I will try to explain them in detail as much as possible. So the first video is about word vectors. What exactly do they mean and how we can understand some kind of mathematics behind them. So before that, what is our goal with word vectors? So we have this problem of trying to encode the meaning of a word in vectors. So there are multiple ways to do that. So just basically, I'm writing the problem statement, which is representing the meaning of our vocab or our list of words, how to do that, representing the meaning in some sort of a continuous vector or something. So earlier there used to be multiple ways of doing that. People used to find meanings using different kind of sets. So one of them was a word net. So word net, what it does was it contains a set of synonyms and hypernyms. For example, Uh, if you are asking, give me the synonyms of good, it will give you something like great, proficient, excellent, or something like that. So it will return synonyms and antonyms and store a lot of such information. But obviously, you can find out that there are issues with this approach. So you can quickly think of several issues like the context matters. You cannot always use words like proficient and excellent in every kind of situation. Like you have to think about the entire sentence, then make your decision. Another thing is it cannot handle no new words. Suppose some modern word is getting added to or appended to a dictionary, right? And recently Oxford has updated their dictionary and we have a new synonym of the word good. How are you handling that? This is a manual work which leads to it being very subjective as well as very manual in terms of the effort being put in to maintain this information. Now, when we had traditional NLP, the words in it were used as discrete symbols. So what I mean by that is basically one hot vectors. So suppose you have a vocab of V or yeah, and then you can have multiple different vectors. For example, we have a vector for king. When you are encoding it a one hot fashion, you can write it like this, and the dimension of this will be V. So there will be V elements in it, and wherever king is there, we will have one, and apart from that, it will all be zero. Now, suppose there is another one hot vector for men. You will see that it will be completely different from king. Now, suppose you want to do a similarity search of it. You want to see how similar king and men are. And since these are vectors, to find out the similarity between vectors A and B, you just do a dot product between them. The higher it is, the more they are similar. Or at least we get the direction of their similarity. Now, suppose if we just do king dot men, you will get zero. Why? Because both of these vectors are orthogonal. Basically, they are completely like they have no inherent encoding in them. We cannot find the similarity between them because any two vectors that you will multiply, you will always get zero. So even similar words like king, and even if you have a word like let's say emperor, although we know that these words are similar, using one hot encoding to get the meanings of them, it will be a useless effort. You won't be able to do anything meaningful. So the problem is it is broken similarity search. I hope OBS is recording this video. Fine. So any kind of multiplication dot product we do, it will result in 0, and we cannot rely on WordNet. We have already seen the issues. So the solution is to somehow encode the meaning of the words in the vectors itself. That is what we want to do, right? Such that any two vectors that we take, we can just directly dot product them and find the similarity. So what we want to do is to represent the words by their context, and the meaning to the words will be given by how closely they appear. For example, king vector and emperor vector will be very close in the vector space, right? And when we multiply them together, the number will show that they are very close. So that is exactly what our goal is with word to vectors. So what word vectors are, let's say now we want to define what word vectors are. Word vectors are simply we want to build dense vectors for each word such that the similarity can be calculated by you doing a vector product. So suppose we have a word belonging to the entire vocab, and we want to build dense vectors for each of these words, and we can just, let's say, do a dot product between a word w and wj that will give us the similarity score. That is our goal. Sometimes these are also called embeddings, which is a much more common word that is being used right now since LLMs became popular. So it is an interchangeable definition, word vectors or embeddings. So one of the first framework for learning word vectors came out a long time ago. It was called Word to Vec. You can search for the official paper. I will try to put the link in the description as well. So it is a framework for learning converting word to vectors. The idea is simple. We have a large body of text, you can say large corpus of text, and then we want to represent every word by a vector, right? And what we want to do is we want to travel through each word, go through each T in the entire text that we have, each token, or you can say each word in the text. We will keep a center word, C, and the context word, or you can say outside word, O. It's also called outside word. And then we will use similarity of the vectors C and O to calculate. The goal is to calculate probability of outside word given the center word, or the vice versa, probability of center word given the outside word, right? This is our goal. And we will keep adjusting these the word vectors, to maximize whichever probability we select. So the goal is to just keep on changing, keep on optimizing the vector such that the probability of outside word given a center word or probability of a center word given an outside word keeps on increasing. The goal is simply this. So let's look at first what we mean by outside word and center word. Let's say we have a word T, and these are the neighboring words T plus 1, T plus 2, and we have T minus 1, T minus 2 as well. So this is a window, right? And suppose this is our center word. Now, if we are looking at the T plus 1 word, we want to find out the probability of WT plus 1 given the word T. Similarly, we want to find the probability of WT plus 2 given the word T. And same goes for here. WT minus 1 given the word T as well, right? We want to find this. To write it more generally, we want to compute WT plus J given a word T, right? Now, and this keeps on being done for each T that belongs to T. So we will just keep on moving the center word across the corpus, And we will be doing this for each token or text that belongs to the entire corpus that we have, or entire piece of text that we have. Now, we can quickly move on to the objective function. So right now you may have an idea of what the objective function will look like, what exactly that it is that we want to maximize or minimize for this problem. So suppose we have a word T, and it will go from 1 all the way to T, which will be our entire corpus. And let's say M is our window size, and we have a center word WT. We have let's say a list of parameters, proper, you can say table or a group of parameters theta, which will be all the variables, or you can say parameters that need to be optimized, right? Now we will calculate the likelihood. Very simple concept. If you have a prior experience in machine learning, you will see this word likelihood getting used a lot. So likelihood given the parameters theta will be, we will be going through all the words where T is our center word, and then we will go through the window that we have, and the probability we want to maximize is WT plus J given WT. So we are just multiplying all the probabilities together, and the higher it is, the higher likelihood we have of the data coming together. Now, what our goal is to maximize this thing, but when we have optimization algorithms like gradient descent or whatever you are using, they work well with uh, minimization problem statement, not maximization. So we will just take, we'll just uh, do this thing. So we want to minimize negative likelihood, minimize, this is called negative likelihood. Now, what generally we do is we take a log of it. So instead of products, this is a product multiplication, right? Instead of doing this, we just minimize the negative log likelihood of the problem statement or objective function. So our final objective function becomes minus 1 by t of log likelihood, which comes out to be minus 1 by t, goes from t equals to 1 to t. We have minus m j, and j not equals to 0. We are not trying to look at the probability. Let me write it here as well. What it means that we do not care about probability of word t given the word t. That is not what we want. So that we are skipping that thing. And here we will have log probability of wt plus j given wt. Very simple to understand. Now the goal is to minimize this function. This is our objective function that we want to minimize. What we are also doing is we are also normalizing it or taking the average over the corpus. It just means that the size of the corpus will not affect our loss function. So suppose we have a very big corpus, it should not be the case just because it is very big, our loss is very high, and that should not be the case. That is why the size needs to be normalized before moving forward. So this is what we want to minimize. I hope it is clear, but just keep it in mind. A very simple to, you know, find the or set the objective function, very simple to do that. Now, one thing you may have observed that the common thing that we have in objective function and likelihood, it is probability of some wt plus j given the word wt, where wt is a center word. The question is how to find out this, how to get this probability, because once we get this, we can easily calculate the objective function that we want to minimize. The solution that we have in hand, very easy to understand as well, is to maintain two vectors. We'll maintain two vectors per word in the vocab. We will have a vector, let's say VW, when the word W is, when W is the center word, and we will have a vector UW when W is the context word. You can use single vector for all of this, but we will be using V and U for a single word just because it is much easier to understand, and we will be able to go through the details very easily compared to just maintaining a single vector. And you must already remember that O is our outside word, C is a center word, right? Now, to calculate the probability of outside word given a center word, which is basically what we want. Probability, this is our outside word and this is our center word. So we want probability of outside word given the center word. It can be calculated as e to the power when we have an outside word. So O is our outside word. So we will be using our U vector, and the center word is C. So when C is the center word, we will use its vector V, and we will just sum it over the entire corpus to normalize the probability. So we will go through the all the words in V and we will calculate the probability similarly, like U W transpose V C. This will give us the probability of outside word given a center word. Very easy to understand. We are just normalizing over the entire vocab. This is our outside word vector. This is our center word vector. And we are just normalizing over the entire dictionary as well. Now, the higher this product is, UO times VC, the higher it is, the higher the probability of them being similar is better. So suppose we have a word, uh, we have a sentence called the cat sat on the tree, right? So cat and sat, they are very closer to together. So this is, let's say, our WT, this is our WT plus 1. And for cat, we will have two vectors. One will be when it is the outside, uh, when it is the outside vector, when it is the center vector. Same goes for, let's say, sat, we will have U sat and V sat. Now, when we want to calculate if sat and cat are similar, we will just do a dot product of US transpose and VC. The higher it is, it will just signify that cat and sat are much closer. It will compute the similarity between outside word and center word. You will also observe that this looks very similar like a softmax function. Not very similar, it exactly is a softmax function. This will give us the probabilities that we require. Now, what we want to do is to somehow train all the, or optimize, you can say optimize instead of train, optimize theta such that we want to minimize the j theta that we defined earlier. And theta is our all the model parameters. Now, the question is, what exactly is theta? So you will have, you have to remember that for each word in our corpus, we are maintaining V and U when it is a center word or outside word. So this is basically what your theta is. This is the parameter of your model. These are all the parameters that you need to take care about, right? So theta is nothing but all V and U vectors of your entire words. So suppose D is the dimension of your embedding. What exactly I mean by that, let me also explain. Suppose we have a word like cat. So cat can be represented by a vector, and let's say it is 0 0.1, 0 0.2, minus 0.5, 0.4. This is four dimensional. So we say d equals to 4 in this case. Now d can be anything. It can be 100, 512, 1024, anything. Now, just to calculate the size of theta, I am saying that theta is in the dimension, or it will have 2dv elements. So how it how we arrive on this number is v is our vocab size. Do not confuse this with v vector. I'll start writing V like this so that we don't get confused. V is the vocab size or the dictionary that we have, or maybe let me write it in a better way. This is the dimension that we will have of theta. D is our dimension, and 2 is just there because we have a v vector and a u vector for each of the words. So each word, which is each word belonging to our corpus, has two vectors, and each vector has d dimensions. The total number of elements or total number of quantities that you need to train or optimize, they will be 2 times d times v, right? And how you can do that? You can simply um, use gradient descent, the time tested algorithm, to optimize any kind of parameters that we have. So let's say theta new will be equals to theta old. Theta will be our metrics of all the parameters that we have. And then we can just take the gradient of it and update our weights, where alpha is a learning rate. So if we are just looking at one of the element of theta, so theta j new will be equals to theta j old minus alpha, and the partial differentiation of theta j old on j theta. So this will be our update rule. So j theta, it is the function of all the windows in the corpus, right? So we are just focusing on one center word, and we will just go through the center word in the entire corpus. So you will observe that j theta is very difficult to calculate. Why? Because for every center word and every context word, we will have to calculate a normalizing factor. So suppose you have, let's say you have 100 words, right? And your window size is 2. And right now you are on some word T. So you will be caring about two other words from it. So this is our T plus 1, T plus 2, T minus 1, T minus 2, right? And you will care about these two words because they are lying in these four words because they lie in your context window. Now, for each center word, which is this, and you will be doing this 100 times, you will have 100 center words. You will be calculating the probability of 1, 2, 3, and 4. 4, you will be doing it for 100, and for each center word, you will also calculate the probability of all other words with it. So probability of, let's say we'll also calculate probability, not probability, but at least this particular multiplication that we have in the normalization factor, we will do it for each center word and each of the context word as well. So there are, for each word, there will be 100, let's say 100 context words. So 100 times 100. So that is huge amount of multiplications that we need to do just to calculate the probability. So it is very expensive to compute, and just for a single update, you will have to wait for a long time. So the solution is to just use stochastic gradient descent. So you can sample multiple windows and update after each one instead of going through the entire batch at once and then updating the weights, right? So use stochastic gradient descent, take out one sample, update the weights at a time. It will be a bit bumpy, but it will work. Now, going to the variants of word to vec has two different variants. The one is first is called skip grams. Skip grams is basically what we saw, where we want to predict the context words based on a center word. And the second model is continuous bag of words model, where we have a bag of context words and you want to predict the center word. So in this particular video, we have and will be looking at skip grams model, much easier to comprehend and understand, right? Now we have understood what is the objective function, how to get the probability, how to minimize or maximize whatever we want using gradient descent, right? What kind of models we have for word2vec. The only problem that you can see is we have huge amount of multiplication problem that we have. There is a unique approach to how we solve this huge amount of multiplications that we need to do, at least for the normalization factor, right? It is called skip grams with negative sampling. The idea is not too difficult to understand, but it does not make sense for somebody who is looking at it at the first time. So we already know, let me just write it again. So probability of outside word given a context word, it is e to the power when it is the outside word multiplying with the center word vector, and then we will just sum it over all the words in the vocab. So we will have UWT This is what probability is. Now we already understood that this normalization term, it is very computationally heavy and it is very slow. So the solution is to use negative sampling, where the main idea is to train some kind of binary classifier. So main idea is, let's say we train a binary classifier, and the goal of it is to differentiate between a true pair and a false pair. Okay, when it a little bit confusing to understand, but the basically the main idea is, suppose you have a sentence, again, the cat sat on tree. Now if let's say we have a window size of 2 and the center word is sat, then when we are making the pairs of it, the pair will be sat the sat cat sat on sat tree. So these are true pairs given a center word. Now let's say somewhere in the corpus you have some other sentence, and we take out some words from that and make a pair. Sat, let's say London, sat stars, sat, let's say Earth, and sat, and let's say ocean. These are fake pairs. And each of these words, sat and including the 8 other different words, total 9 words, they will have their own word vectors, U and V, right? Two word vectors, depending on the situation. Now, the goal of that binary classifier and the objective function that we will decide on this problem statement um, is to basically identify whether this particular pair is a true pair or a fake pair, right? And in solving that problem, it will modify the vectors u and v in such a way that we can solve this problem, whether it is fake or not, and something like that, right? I hope you understood my point. So we will train a classifier whose goal is to understand whether a pair that we have been provided, it is a true pair or it is a fake pair. So we know normalization is expensive. So instead of like finding the best high probability context word given a center word, we calculate whether a pair of word is true pair or not. So we sample k random pairs. So this is what k is. In this k equals to 4. In this particular example, k is 4. So from the entire corpus, we are sampling 4 words and making a pair, which will act as our fake pairs. And for a given true pair, we'll be sampling k different things. So each time we arrive on a true pair, we will be sampling k. So suppose you will have 2m plus 1 true pairs, and for each of them you will be sampling k. So there'll be around 2m plus 1 times k pairs that we will need to look at instead of the entire vocab. We'll go to the exact numbers and details. So suppose um, in the earlier case you were calculating probability, you will have to go through each word belonging to the vocab which is used. It can be like, let's say, a billion. But instead, if you have, let's say, a window size of 2 and k equals to like 10, each time you are calculating the objective function of probability based on negative sampling, you are just looking at 2m plus 1, which, and then you are also sampling k vectors uh, each time. right? So this number is much smaller than a billion, much, much smaller. So this reduces the time taken to train our model by a lot, by a factor of maybe hundreds or thousands, right? So just to summarize the idea, we take k negative samples, which are fake pairs. Then we will also take uh, we can use the word probability. The, Let me rephrase it. So how will you sample k negative samples? You can just take the probability of them occurring in the corpus and randomly sample them out. So you can use in Python it is random dot choices. You provided the values that you want to sample from, their probability map, and how many values do you want to sample. So you can just get the k out of them. So the probability map can be just calculated as the count of the word upon the total number of words. And this way you can sample k words, but that is not important. The important thing is we need to somehow randomly sample k words, and none of those words should be our center word. That is important to understand. So you need to ignore the center word. So the word belonging to the k next samples, it should not be equal to whatever center word that we are right now looking at. Now the goal is to increase the probability that real outside word is there. So real outside word appears. And to minimize the probability that random word appears, or you can say noise appears from the negative samples. This is our goal. So I'll just quickly write the objective function and then we can look at it. What exactly does that mean? So objective function will depend on our outside vectors and our center vector of this. Now we will write the objective function minus log of sigmoid. It is UOTVC, and we'll just go through each of the word in our negative samples and then calculate log sigmoid of minus when it is the outside word times again VC. It is a bit complicated to understand, but let's look at with an example. So this thing is for real pairs and this thing is for fake pairs. So suppose we have some real pairs like cat and sat. So when we do their multiplication, let me also make the graph of sigmoid. So here it is 0, here it is 1, and at 0, I hope I have made correct. So what it is, 1 plus e to the power minus x, it is half. Here we have it as zero point 0.5. This is what sigmoid looks like, right? So suppose this number is very high. Whenever we are multiplying the vectors of real pairs, this will be very high. So sigmoid will be 1. When we have a very high number, let's say 10, sigmoid of 10 will be much, much closer to 1 and log of it will be 0. So we will be getting 0 here. And suppose we have a negative sample and the model is somehow it is saying that the similarity between the negative sample and the center word, it is much, much higher. So this thing, UK times VC, it is also returning 10. Now we have a minus sign, so it will convert it to minus 10, and sigmoid of minus 10, it will be much more closer to 0, something like let's say 0.0001. And if you remember a log graph, it looks like this. Here it is 1. And as we get close to 0, it starts exploding. So the loss will be much higher. It will be like 1,000 or something, right? So it is heavily penalizing the model or the vectors that we have when fake pairs in the center word are closer. Now suppose um, it is the opposite case where the correct pair that we have, they have a very low number. So suppose the similarity between correct pair is coming out to be, let's say, um, very low, like very close to 0. Sigmoid of 0, let's say it's zero point 0.5. or not, let's not take 0. Suppose it is coming out minus 100. Sigmoid of minus 100, it's almost close to 0. And log of 0, again, it explodes and goes towards a very big number. So it will, again, minus times minus a very, very big number. It will give you very heavy penalty on having wrong vectors for real pairs, right? So this is how the loss function is designed for this particular problem. So we will, for each pair, you will observe that there is no sigma here. So we are just looking at one pair at a time, right? And we are sampling k negative samples for that and just calculating this particular loss function. And once this is done, you can again optimize it using gradient descent or stochastic gradient descent and so on. And this is how negative sampling works. Now, what I want to do in the next particular chapter is we can go through how backpropagation works, or maybe how RNN works, how n-gram language model works, or we can look at implementation of this different you can say concepts in PyTorch. Yeah. So this is it for this lecture or this session. In the next one, most probably we'll be going through n-gram and the implementation of skip grams with negative sampling plus n-gram, uh, how to implement that in PyTorch or NumPy, whatever I decide. We'll see later on.